and then sometimes they ask you to draw both Q and Q prime. So why don't you screenshot this example and then try to do it maybe within 5 to 7 minutes. This one should be bigger. And then the way to make answer, you just take a line. For example, you think this is here, make a bit bigger, I think. Right. Okay, so like that. So if you think this one will be upper, and then just do like that, and so on, and then make the vertical one. So vertical one like that. This is example. So you can check from your truth table or the SR flip-flop. This one indicate, the circle one indicate what? If you remember yesterday. What is the circle one present for? It is active low. Okay? Active low. So try to answer in 5 minutes. Just draw the output at your own PowerPoint or your own PowerPoint, and then maybe someone can share. Have you a screenshot? Okay. Okay, I think everybody uh, successfully did the example. Anyone want to share? Anyone want to share? So for, let me share mine. Because everybody very silent. Okay, now you see S and R, and do remember sometime the what call question, the exam paper maker put S at the top, R at the bottom. So do remember to aware with the tag. Okay. So now we have 0, 0. Okay, for in my advice, what we do? Uh, maybe uh you should tag the location where is the prohibited region first. Prohibited region. So for prohibited region is 0, 0 here. 0, 0. So you see where is the location of 0, 0. So we have this one, and then this one, and then this one. Relocation of 0, 0. So what do we need to do? Because we know at prohibited it will give the output high, and then we place high. Then you just copy and then put here. Same goes to this one. Because of this, we only look at Q, so we only care about this one, about this, about this column only, or Q column. If we have 1, 1, we have toggle, we have whole. Okay, so finally this one have the whole region, and then this one also have whole region. And then after we finish with prohibited, we just go for set uh, set region where is S is 0. So we already settled about 0, 0, so we not need to care about this one. So we just observe where is the location of set is 0. So this one set is 0. So it looks like it will give us the output high. So what you need to do, you can just extend this one. And then S is 0 also here, so it will become like that, output 1. And then how about this one? This one is S is 1, R is 0, the output is Q not Q equal to 0. So this one is Q to equal to 0. Same goes to this one, Q equal to 0. And then after that is 1, 1 is whole. So the Q is remain at 0. Like that. So this one also in the reset mode. So it should be 0. And you just copy this one. Put here. Okay. And then goes, and then at the end, 2n is hold mode, so it just hold the 0 value. After that, you just put the vertical one like this. Do you get the same answer or not? So this is what you get for the T-flow. If the circle is not present, so this one will be this one will be flip. The Q and Q prime will be flip. If what we call if it is active high. Okay, if I input. But for this one, it not have any clock, so you need to depend on the clock. Okay, you need to depend on the clock. Okay, so this is the example. I hope you get some idea how to solve the output signal if the question is given as shown. So now we continue with our next class, which is counter. So in this counter, so in this counter topic, we look how can we use flip-flop as a ripple counter with waveform, and then ripple counter down, like just in New Year celebration, 5, 4, 3, 2, 1, like that. And stopping counter when we count to 10 and it stop. And frequency division counter, we divide the frequency of the signal using counter, and then how to use the counter IC. Okay, now we going to go on overview of the counter. Counter defined as one input clock. The output followed from the defined sequence of the clock, and also the connection of the circuit. The common task for counter is to count up 1, 2, 3, 4, 5 above, and or count down decrement count down from 10 to 1, or for increment or decrement count, that one just for time. And then for sequence event, meaning that you want to fill something in the box, maximum quantity in the box is 12. After 12 plastic food or 12 can of food fill into the box, and then the box move and the computer reset the count again from 1 to 12. That more on the sequence event. Or divided frequency. Let's say we have 1000 hertz 1000 hertz square wave frequency, and then at the same time you need to have 500 hertz square wave, and then also 250 hertz square wave, and 125 hertz square wave. So we can use the counter to divide the frequency of the input to get several other frequency. So the counter also become address memory, and as well as temporary memory. So that is the brief idea on the counter. So the characteristic of the counter depend on the number of bit, whether it is 4-bit counter, 8-bit counter, etc. So for 4-bit counter, maximum count is 16 value. However, for 8-bit will become 128, if I'm not wrong. And 256, 3 power 2 power of 5 is the 2 power of 8 is 256. Okay, 256 numbers. And then they have a modulus of counter number of state, whether it is decade counter number, count to 10, or 4-bit counter number, or 8-bit counter number. We can also purchase for up or down counter, whether it is asynchronous or synchronous counter. We also can set for presettable counter. Presettable counter. And also self-stopping counter. So now we are going to see on the ripple counter. In the ripple counter, the ripple come from the clock input. So in the, if you see here, for the counter, no, most of the time we are using JK flip-flop, because yesterday I mentioned that the JK flip-flop have the function of toggle to switch to the opposite mode. Okay, that is the advantage of JK flip-flop. So when signal come, it can flip. Oh, just now 0, when something come become high, and then another coming signal goes, it down again. Okay, mean that one cycle in JK flip-flop toggle equal to 2 signal input. Okay, so from that we can have a basic counter. Okay, so let's say we give the first signal. In this condition, to have a function of the toggle, we should what we call give a high at JK and also high at the clear and preset, because all of JK is active high and preset is active low. Okay, so JK flip-flop is in the toggle mode, and then because this one is negative age, if you see at this part, this is negative age. So when the first pulse come, and then the pulse goes up, and when it down, and then when it down, Q start to change from 0 to 1, because it's in toggle. So 1 goes here, become 1 here. And then 1 also goes to this clock. However, it's still up, going up, it's not yet coming down. Okay, so what happened? When second pulse goes, and then the Q will be converted inverted from 1 to 0, and then the first state will become 0, and then the Q just now from high, and then suddenly signal becomes 0 down, and then the Q at the second JK will change to the toggle from the in the toggle mode from 0 to 1. So you get increment from 1 to 1 0, and then signal 3 come, increase, and goes as usual until become 1111. Okay, because this is for binary 4-bit binary. On the next clock, pulse 8, all flip-flop will be toggle. And then it become 1000. Okay. Toggle, and then become 1000. So it can count to 16 state. Okay. The counter has a modulus of 16. Now, just now we just see in terms of pulse in terms of arrow. Now we see how the ripple looks like. Okay, so the first stop is the clock input. We give first pulse. So this is a first pulse, and when first pulse coming down, this is the Q. First output Q here is increasing, and then increasing. The second pulse coming down. This one maintain high and start to turn down, and then it will trigger the output for the third one, the second place. The second place going high, okay, and goes as usual and become longer. So the clock toggle the first flip flop. The first flip flop toggle the second one toggle the fourth. Okay. So if you can see here, the frequency of the first flip flop, second flip flop, and third flip flop will always shorter than the clock. So the first flip flop, the frequency is half of the frequency of the clock, and then the second flip flop, the frequency is half of the first flip flop, or 1/4 of the first flip flop. Okay, second of the clock. Why we know it 1/4? Because here you need four pulse. Four pulse is needed to make one pulse, so the frequency will be 1/4, a quarter of the early frequency. So this one, just like I showed previously. To remember the connection of modulus, just Q go to the clock, Q go to the clock. We only use Q. This is also just like counter up. Counter up mean that we calculate the increment. And then now we want to change that one to become decade counter. We only want to count up to 10 only. So what do we need to do? We need to do what we need to do. We need to tap, because 10 is 1010 in the binary. So when it hit 1010, it will reset all the flip-flop, and then the binary will become 000 again. So now we start at state number 8 equal to number 7 in the state 8 is equal to number 7 in the decimal. So 111 is 7s. So we will connect because 10 equal to 1010. So when it hit 1010, it will change, become 000. So we need to tap the value of 1 at 8th place, and then the value of 1 at the second place here. And then we put that one when high, when 1010 state 1010, high goes here to the NAND gate, high and NAND gate become low. So when low go to the clear, what we call clear pin, what happened when it go to clear pin? To remember again the previous flip-flop, we go to JK flip-flop. Oops. Okay. When clear is 0, but preset still 1, clock and JK is irrelevant. The Q will turn to 0. All Q will become 0. So it is same like this one. So when become 1010, and then it goes to AND gate, NAND gate become give output 0. 0 will hit the clear pin, and then all Q will become 0. When all Q becomes 0, it gives 0 at the binary output. So let's see how this simulation look like. So now from the 7 and then give another signal 8. This one is 1000 equal to number 8. And then this second pulse we equal to number 9. And then when we hit another pulse, it not show 100, 1010, but there's only very short time for 1010, and then it become 0000. So this is decade counter. It only count up to what we call up to 10 only. So when this binary becomes 000 and 0 goes again to the NAND gate, and then the NAND gate will give output high. High go again to the clear pin, and then the JK flip-flop will be set in the toggle mode again. So when we get pulse, it will count to 10 again and repeat. So like that. So it take from the modulus 16. We just embed. We will just connect with the NAND gate, and then we get decade counter counter for 10. Now we want to have counter down. A counter down. In the counter down, we want count down. Okay. In this case, maybe I do not know whether let me see who in the class now. Iza, have you went to any New Year celebration or not, Iza? Huh? Have you ever experienced went to New Year celebration? Counting for New Year?
Ya, doktor.
Ada?
Tak ada.
Oi, too good to be true, but you are good. Okay. How about Sarah? Oi, kelas ni semua bagus lah. Tak pergi tengok. Tak pergi tengok.
Pernah, doktor.
Pernah? Bagus Sarah, pernah. Okay. So, so when Sarah went to what we call to New Year celebration, of course, when it near to 12 midnight, and then they start to make counter down. Okay. So we can also perform that counter down using JK flip-flop. However, in that counter down, let's say from 5, 4, 3, 2, 1, and then after 1, what happened? Actually, it just come out Happy New Year. It goes to 0 and it not go to -1. It not went to -1. So that one is considered counter down, but self-stopping. But this one only counter down, down counter. So in down counter, only we still use Q output at the binary output. However, the clock for the second and the third flip-flop, the third JK, is used complementary from the first from the flip-flop before. So for the first the first flip-flop will give we will connect the complementary output to the clock of the second flip-flop, and then same goes to the third flip-flop. So how it what happened? What happened? So let's say we have first 111 initial state, and then we give another pulse, the output will become 0. Okay, pass down, this one become 0. 0, and then this one not changed yet, okay? And then when this pulse coming down, this one become 1, and then this one trigger from high to low, and then from 1 become 0, and this one goes to here. From 1 become to 0, and then this one is 1, already at high state, okay? Goes down, become 100, and continue until 000, okay? When 000, it become 1 again. But that one is just countdown, not self-stopping, okay? So the connection almost same, except the input of the clock input for the second and the third flip-flop is from the complementary pin. Now self-stopping counter down. Yeah, based on what I mentioned just now. So we add here OR gate with 3 input if our counter is only 3 bit. Okay. So when become 000, all three become 000. So 0 go to the OR gate and give the output 0, and 0 go to J and K. So what happened when 0 go to J and K in this condition? You go to the truth table again. JK flip-flop. When JK, we have clock, but JK is 0. So what happened? No change. So the time maintained at 0. So it's not like Sarah, when Sarah go to the New Year celebration, when count from 3, 2, 1, 0, -1, and then Sarah will think, oh, I getting younger because the time is reverse. Okay, so we do not want to have that deja vu style. So we need to put self-stopping at this down counter. So by adding OR gate, this OR gate, the function is to make the first flip-flop in the whole position. So maybe you are thinking, why we not put at the second and the third? Because the second and the third depend on the output from the first JK. So we only need to tackle down the JK from the first flip-flop. So not need to interfere the others. Okay. Okay, no change. Okay. Now we use counter as a frequency division. This one I shown in the first Ripple just now. We still use modulus 16 counter. So the configuration is same, but we not interest on this one. We not interest on the output. We do not interest on the output signal. So, but we know that when we give a hit 800 hertz square pulse, the first one will become 400 hertz frequency. The signal from the second flip-flop become 200, 100, and 50 hertz. So meaning that from 800, only one frequency, you can have another 4 frequency of divided by a number of bit, 2 bit, 1 bit, 2 bit, 3 bit, and 4 bit, depend on the number of your counter. However, you can in this configuration you only get the frequency of the lower frequency value. You cannot increase the frequency by using this configuration. Okay, so the counter only make us possible to obtain lower frequency from the input frequency. So if the input is 3200 Hertz, so the first place we will get 1600, and then 800, 400, and 200 Hertz. Now we will see how do we want to use counter IC. Okay, because our life is already difficult, so don't make our life so difficult by try to choose a single flip flop and to make a connection. Yeah, of course you can do that, but if you just want to have that type of 4-bit counter, you can just have this 7493 counter IC. So from this, you have two input clock, JK input here, JK input A, a clock input A and clock input B. And then NC mean not connected. NC is not connected. The IC have the VCC as an input voltage and the ground to power up the voltage. And then we have QA, QB, QC, and QD for output. And then we also have R0. R0 here. R0 here for what we call let's say we go for the data sheet. Right. Oh, so this one is wired as a 4-bit binary counter. Okay, so 7493. So this one binary counter, we have QA, QD, QB, and QC. And then what is RG? What is RG? A moment, please. Oh, that's one is reset. Reset button for preset and clear. Okay, so reset this one is we have in see we have in here is what we discussed is 7493. 7493 it has R01 and R02. Okay, R01 and R02 only. And then we have two type of input A, input B. It is negative H trigger. It is negative H trigger. So here is negative H. So we can have two input. Okay, we can have two input clock. And then we have R01, R02, and also R91 and R92. So let's see what is R91 and no. Because for that one, for above one, that one to reset more, to have more reset. But for this one, we have only R01 and R02. So let's see how the connection. Oh, this is 493. 493. So if we only want to play as to connect as a modulus counter with a single input, we only use input A. So input B is not necessary. Input B is not necessary. If we, so what do input B did? Input B, because if you remember on this one, oops, okay, the input B come from the clock flip-flop clock 1, the output 1 from the first flip-flop, so it go to input B. So if you see from this diagram, so this one QA and the first clock is not connected, but the B, C already connected. So you need, if you want to make a system modulus counter, we need to connect QA to input B. So it just we put a wire between QA and input B. And then if you see here, RA is the NAND gate. R0 1 and R0 2 is NAND gate. So if you want to do as a 10 decade counter, you need to have a D1 and B1, and then this pin you will connect to R0 1 and R0 2. So you just give this input, and then it will run as the decade counter. Okay. And then for this one is for 7493, and for 7490, you have more flexibility. You still have what we call four JK flip flop. However, it is sum of the 2 NAND gate and also OR gate, mean that you can use as a ripple counter, as a ripple down self-stopping. You can use as a self-stopping counter, and also you can use as a decade counter by connection that you like. So how to, if you do not want to make your life so difficult, you can understand from this one. This one is binary conversion decimal sequence counter. So if we put zero value, so we get this kind of output, high low, and then this one is binary quinary output, and then this one is counter sequence. This one is counter sequence up to 16, and then you also have a set and count function also. Set and count function also. So it also give note for this one, for Q993A. Note output QA is connected to input B for BCD count. Out QD is connected to input A for binary count. QA connected to input B. Okay, so you need to see the note. Okay, you need to see the note. Okay, so that's all. Not at least you get some idea on it. Okay, you get some idea on it. So, and then when you see this one, you can have some familiarization. And then in this case, why did they connect R0 1 and R0 2 to ground? Why? Because it want to have a toggle function. Why toggle function? So when this one is ground, and then become high, or go to all clear, and J preset already set as high. So but clear we need to set at high. So this one will behave like a counter, and it will run as a toggle mode. Okay. So we can use this IC as a frequency division too. So this one is magnitude comparator. Magnitude comparator, you have two binary input from A and from B. Okay, the function of magnitude counter, it just give the output which one is high, whether is A value binary is high than B binary, or it's same or it low. That's all the 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 answer that they give. Okay. So this is the function of magnitude comparator. It just compare the magnitude. So let's say this one is 0101 give to A and 0101 give to B. So answer, we will get output high at A equal to B. And then same going to the others. Okay. And then the simple troubleshooting I already shared with you previously. So that's all for the counter. So for the counter, what we learn, we have a ripple up counter, and then we also have a ripple counter with waveform, and then how to connect for the ripple down counter, how to connect for the self-stopping counter, and then how can we utilize counter as a frequency division, and then example of 7493 counter IC, and then what is the function of the magnitude comparator. Okay. Okay, we take 5-minute break and then we will continue shortly. Oh yeah, yeah.
Nak tanya boleh?
Boleh, boleh.
Yang untuk ripple counter tu kan, dia
Okay.
memang akan, kalau pass one tu dia memang akan masuk dengan low dulu kan?
Biasanya bila kita,
Macam mana?
okay, okay, get good question. Is that the incoming signal start from zero? Okay, the answer is yes, because we not hit the switch yet. So in normal condition, as long as we not hit the switch, it's still zero. And then when we hit the switch, and then the pulse start to come.
Oh maksudnya kalau dia masuk dekat dia pass 1 sampai, lepas tu nanti dia masuk kosong. Lepas tu nanti dia lalu dekat JK tu, dia jadi 1.
Okay, in the beginning it's still zero like this. Okay, but the graph is inverted because time is travel like that. But the pulse come first, no signal. Okay, the no signal is already passed and suddenly signal come. But this one time is travel. So but we draw it invertly. So in the beginning, let's say from 1 to 2 seconds, you not hit any switch, any button yet. So it still remain at zero, and then when you hit the start button and it go up. And then the pulse start running.
Oh.
Okay, so that's why in the drawing we always put zero first, the low level first. Okay, in the drawing. But can you do directly from high level? Of course you can, no problem too.
Terima kasih.
Okay. So we take 5-minute break. Okay, we'll continue a bit on the. Actually, you have one more slide, but this one is of course is not covered in the. I speak directly. It's not covered in the final exam. Final exam, but I'd like you to have a brief idea uh, on what is chief registry. Or you have USB. What is USB stand for?
Universal Serial Bus.
Yeah, universal serial bus. And also last time you also have a parallel connector in your old computer, but now most of thing we are using USB. So that one is called under that type of connection. We call under shift registry. So we have several type. We can have a serial or parallel data conversion, mean that to do the process, and then we also can have a serial loop shift registry or parallel loop shift registry. Normally for CCD type, CCD type camera sensor, the information captured by the CCD is sent line by line, line by line. So when the first line already send the data, and then the upper line will go up, the whole signal will go once up and then send, but it's sent line by line. However, in CMOS, it's more faster because it can deliver the data not single line by single line, but it in parallel registration. So the data shift data storage is more faster, so we can have more what we call faster frame per second of the image. That is the easiest example. Okay, so seems like your computer. Last time you have solid state. Last time you have HDD. HDD is one single scanner. So your hard disk need to spin, and then you have a magnetic reader. So it's read in almost series, not parallel. So however, in solid state, it can do parallel reading. So data searching or data storage in SSD drive is much faster compared to hard disk drive. Okay, and also more lighter and no movement part. So shift register is a sequential logic device made out of flip-flop that allow parallel or serial loading, that is data coming, and serial or parallel output, as well as shifted by bit by bit, as shifting bit by bit. So we can still use that JK flip-flop in several connection to make sure what we like. We have the data that come in series or parallel data, or we have data that come in series but we want the output as a parallel, those parallel output, or data come from the parallel and we read is series output. So that we need to determine based on the behavior of the data. The common task of shift register is serial or parallel data conversion, UTA as an example, and for time delay mean that in some type of detector, for example X-ray detector, when it is based on the when the X-ray photon hit the detector is commonly from silicon. So what happened in the silicon, it will generate electron hole pair. I think you already learned solid state physics maybe. So when electron whole pair generated. So they give bias, so the electron will go to one side and hole will go to one side, and that it used to charge up capacitor. So because we know it is time tau is needed for the capacitor to charge up. So therefore we need that time delay to ensure all the signal charge up first before make another reading. So that one is process or shift register. So we can use that shift register as a time delay before reading the another next signal. Also for ring counter, twisted ring counter or Johnson counter finally as a memory device. So we have several type of shift register depend on the bit of it. 4-bit, 8-bit or others, and whether it is serial or parallel loading, whether it's synchronous or asynchronous or synchronous. Synchronous or asynchronous is mean that during that time or not live or not live. Okay. A common mode operation, parallel load, shift right series load. The series come like that, and then it shift right. Shift left series load, or as a function of to hold, or as function to clear, like in CCD camera, circulating or non-circulating. So for example, this is data that register used to convert from series to parallel, or reverse from parallel to series. So now is data in series and also output also in series. So you imagine, let's say we take example for the data, one parcel of data is what we call, you have 3 bit here, 8 digit, okay, 3 bit, and then for the data to coming out, to give the output, let's say it take one nanosecond, 1 microsecond, 1 microsecond. So we need for a parcel of data with 3 bit, we need 8 microsecond for the data to be completed transfer before new data coming. How about if our signal is 100 bit? Not 100 bit, 10 bit. 10 bit is 1024 numbers. So let's say it's still same 1 micron. So 1 micron times 1000, you get 1 millisecond, and then you will start feeling the delay. Okay. So what happened? We want to convert this series parcel input to the parallel output. So from this one, from the series output to parallel output, now it becomes still maintain the output is still 1 microsecond, because it take out all the data simultaneously. And then this one is the data come in parallel. A lot of data coming in the single point, but the output give out as a series. Okay, yeah, as a series. So this is example we can set for the data to come in as a parallel. Let's say we have a lot of data in the single in the single time. So, but the data is complement to show that event. So we do not want to break it out. So we receive it as we give output as a series. And also we can have, because the data is independent one by one, we can have parallel in, parallel out. This one is more the fastest. Okay. So the slowest will be series. Okay. So this one will be series in, series out. How about this one? This one is parallel in, series out. So this one is parallel in, parallel out. So series data registry, okay, this one is combination using D flip-flop, preset, deactivate. So all connect, we not use preset, so it deactivate, and then clock is connected in series with at every flip-flop, and clear is connected also in series, and the data only load at the first flip-flop. So when note that when clock what happened, so now when we give the data in the series, so we get a parallel output ABCD, the order ABCD. This is parallel output. So the input here is data, clock, and clear. So this one is series load. We only give the data in series one by one, and then we get a different ABCD output. Okay, so we get like that. So the clock always going as normal. In your computer you have clock, right? So the data is based on what you give input. Okay, so this is example of a series loading, parallel output. So what we see others, this one is parallel load, shift registry. So parallel load, the output, the input is given at the preset pin. The output is given at the preset pin, and then JK is wired from the it is wired JK is wired from the Q. From the Q is looping, and then the clock is remaining is connected as usual parallel, and also clear as parallel. And then this one is circulating line I mentioned just now. So it pass data from flip-flop D, from D to flip-flop A. So on each pass. So the output is here, but the input is parallel data input. So this one is not used as a counter. So it used as a data registry. So we have a parallel data input. All the data is given at a preset pin, and then we take output at the Q pin. Okay, Q pin. So this is parallel load data. We also have circulating shift registry, parallel data input. However, CD is activated. Okay. So parallel data, when the parallel data input all inactive, so it become like this based on the path tree. So it just rotate like that, just counting down. Okay. And then finally, we can have a universal shift registry IC. Okay, shift registry IC, it based on JK on JK. Let's say we see first whether this one is JK or D flip flop 74194. Mariam, jangan. Janganlah nangis. Ya. Okay, this is the IC. So let's see what is the logic diagram. So it use what we call RS flip-flop. So in this one, the IC use RS flip-flop combined with AND, OR, and also we have NOT gate. Okay, we have NOT gate. So this is the logic diagram of the IC. Logic diagram. So what you give is the input pin is for particular what we call particular pin at the AND gate. Also, we get Q out, QA, QB, QC, QS, Q out, and also we can have input for clock and also clear. So we have also series shift right series input, and then so this is typical timing. I think you need to, if you want to learn, you need to stay a bit and try to read the what we call the waveform ripple. Okay, so this is the idea on the 74194 IC for shift registry. And then about digital roulette game. Okay, normally this one you get what we call spin wheel input. Spin wheel input, let's say that this one is rotate, and then this one is quite nice. Normally in I don't know whether nice or not, but they use as in game. So power up initializing circuit, refrigerator, and then simulate router display. I think they use in what we call in the game on something just like Mojutaria or something like that. Okay. However, I'm not so familiar with the circulation type. Okay. So that's all for shift registry. Just a brief introduction on what is the function of shift registry and how can we use a flip-flop as a data conversion or to accept data and to give out the data depending on the nature of the data, whether it is series input and we want the series output, or we have parallel input and we want to get a parallel output. So the troubleshooting hint for the IC is still the same. You feel whether it's hot or not, look whether broken, if we smell overheating, and check for the power source and trace the logic gate. And finally, we know the normal operation of the circuit. Okay. So this one is for arithmetic. Arithmetic, I think I do not think I want to continue on this, but this one is quite nice for you to learn, because maybe you want to get the idea on how your calculator adding binary number. Okay, so because you key in as a decimal, but your calculator adding as a binary. So of course you are curious on how it do it. So addition of the binary and decimal is still the same, but the number of the binary only 0 to 1. So let's say that we have 1010, 1010 is 10, and then you have 11 equal to 3, so 10 at 3 you get 13. So this is 13. So when 1110 is 14 and 1111 is 15. So you add 1 equal to 1, you get 0, carry 0, and then finally you get the result like this. But how you do the addition? addition by using this one is half adder. So the addition is just use two gate, one exclusive OR gate and AND gate. Okay, logic diagram for half addition. And then this one if you want to know more on how it going, you can do simulation on the online logic gate simulator, or you can try at what we call at lab if you have free time, or if not, you just read the digital electronic book that being shared in the WhatsApp. Okay. And then this one is full adder. We have fee A, B, and C. So I think this one is quite nice to know how the addition and subtraction of binary works in what we call in your calculator that you use from your high school. Okay. Parallel adding also possible. Okay, that's all for today's. I think maybe we need to have one more class. And then maybe we can finally we can what we call summarize what we learned for the whole semester. Okay, the final one is related to the what we call connecting with analog device. You have digital output, you want to connect to digital to analog devices, and then it is in chapter 14. You can read from the textbook, but I give brief introduction that what we're going to learn is related using op-amp, that what we learned in the beginning of mid-semester. After mid-semester, so we have binary input here. This is a digital to analog converter. So your binary will be this one is example of Swiss, but you're not using Swiss. You use a binary output that give you the digital signal directly. So in this type of example, we use switch, and then when we press the switch, we get the input. Okay, but the connection of this op-amp is as summing amplifier op-amp. Okay, so we want to use that summing amplifier to convert binary digital signal in the binary value, binary signal, to analog what we call analog signal, which is the real voltage that we use in daily life. Okay, the voltage that maybe this 3 volt is to ramp up the DC motor. Okay, so the last topic on the simple DA converter using a summing amplifier. Okay, I think that's all. Okay, before we end, I'd like to log in to slide in